My research project was about prime numbers, and the way their digits appeared. So I mentored under Dr. Bogdan Stoica from Northwestern, and he's a postdoctoral research in the physics department. So he works with like high energy physics and mathematical physics. And we decided to focus on a project in mathematics because that's what I have more interest in. So we decided to look at prime numbers and what patterns we notice in the digits and how many times they appear. For background, we started with Euclid's proof that there's an infinite number of primes. So first, he uses a proof by contradiction, basically assume that there isn't an infinite number of primes or they're finite. And if you list them all and multiply them by each other and then add 1, that new number that's been created isn't divisible by any of the primes that we listed before. So that means that another prime has been created that's larger than all the other ones. And since another prime has been created, we can conclude that there's not a finite number of primes because we just got another one. Then we also looked at primes in the form of 4k plus 3, which is similar to the previous proof, because we start with a contradiction again, assuming that there isn't an infinite number of primes in the form of 4k plus 3. And again, if we list all these primes except for 3 and multiply them by each other, and then if you multiply that by 4 and add 3, we've created another number in the form of 4k plus 3, except this number isn't divisible by any of the primes that we listed before. And then at the same time, we can also prove that all numbers in the form of 4k plus 3 have a factor in the form of 4k plus 3, because when you factor it, it'll be 4a plus 1 times 4b plus 3, which you can see in the 4b plus 3. That's just like the 4k plus 3. So that means all numbers in the form of 4k plus 3 need to have a factor in the same form. However, in our first part, we said that this 4k plus 3 number does not have a factor in the form 4k plus 3. So these can't be true at the same time. So going back to our initial statement that there's a finite number, that can't be true. So for our research, we used Sage Math, which is kind of like Wolfram Alpha. And we created a program that generates a number of primes. So like asking it to generate 100 million primes in base 10, and then we give it the digits to use. Then the program would count how many times each digit appeared in all the listed primes. So like how many 2s are there in all of the first 100 million primes? And then we used it to find the ratio between certain digits. So like how many times does 2 appear versus how many times does 1 appear? And we found those ratios and graphed them against the number of primes generated. So the ratio in the y-axis and the number of primes in the x-axis. And here are the graphs for 2-to-1 and 4-to-1. So you can see like a dip right here and right here. And that's because the first few primes, they all have a 1 at the beginning. Like all the numbers between 100 million and 200 million have 1. So that's why there's a dip, because there's so many 1s at first and it kind of evens out. But if you pay attention to the y-axis, the ratio stays pretty close to 0.7. And here it's also around like 0.62. But then we also looked at 3-to-1 and 7-to-1. And there's a dip again, but also in the y-axis, the ratio is much closer to 1. So here it's 0.95 and it's pretty much almost 1. And here it's close to 0.95. So we can see that 3 and 7 are there more than 2 and 4 are, because the ratios are closer to 1. And we can kind of connect that to like the quality of numbers in general. We know that numbers ending in 2, 4, 6, or 8 are even numbers, which means they're multiples of 2 and they're not prime except for 2. And then numbers ending in 5 or 0 are usually multiples of 5. So numbers ending in 1, 3, 7, and 9 are more likely to be prime than numbers ending in the other digits, which is why there's more primes that have those digits in them. So based on what we know about like the prime quality numbers and the graphs, we can conclude that the quality of being prime is heavily influenced on the last digit of the number. In terms of the research in general, I didn't really have a lot of problems with it. Most of my issues were smaller ones, like not understanding how to use the software, because we did have to code a little bit to use Sage Math, like asking the computer to do the calculations for us. But they were easily resolved. It was like asking my mentor or like Googling it or just messing around. I think it was really cool to learn how research was conducted in math, because usually when you think of research, it's like working in a lab, but this is kind of different. And I don't really get to see math like this in the classroom, because usually that's like applying formulas, or like if they ask a certain question, this is what you need to do. But this is more like abstract and like looking at patterns and what do they mean. So I think this is really cool to do. And I definitely want to try something like this again, maybe in college. Yeah, thank you.